Hello, everybody. Welcome to our lecture on hyperspectral anomaly detection. In the last lecture, after discussing hyperspectral classification, we have already started discussing about hyperspectral anomaly detection. The hyperspectral images, as we know, provides us with rich spectral information with its hundreds of bands that of course vary depending on the specific sensor that we are talking about. However, this rich spectral information enables us to detect the materials that exhibit unique spectral signatures. It enables us to detect subtle spectral deviations, and thus it enables us to detect small objects or to detect anomaly in a large background. We have also discussed in the last lecture briefly that how the anomaly detection problem is different from target detection. In the case of target detection, we can assume that we have a given target signature. However, that is not the case in the case of anomaly detection. In the anomaly detection, our assumption is that we are working with unknown targets. And thus, in the case of hyperspectral anomaly detection, the focus is on spectral rarity. That of course doesn't mean that our focus is just on the spectral signature. We also need to take into account the spatial context. That makes, of course, the problem even more challenging. And thus overall, this hyperspectral anomaly detection problem is quite more challenging than supervised target detection. The challenges in hyperspectral anomaly detection include that fact that we do not have generally any labeled data of anomaly. If we had, this is the anomaly that we need to detect and this is its like corresponding training data, this would rather become target detection problem and won't be anomaly detection problem. So, as we mentioned before, that we have to depend on spectral rarity, our approach would be to somehow model the background distribution and then to understand, this particular pixels, they seem to be farther away from the background distribution. However, often it happens is that the background distribution itself can be highly complex, especially if you think about complex urban areas and all. In that case, the background distribution can be highly complex, and thus just understanding the difference from the background distribution is not that easy, in the sense that we have to first model the background distribution, which itself is complex. And on the top of this, the anomalies can be quite small in size, and thus they can be quite difficult to detect. Furthermore, atmospheric effects and presence of cloud and similar phenomenon can further complicate our analysis. Additionally, we have to keep in mind that hyperspectral images contain hundreds of bands. This is, of course, which is enabling us to detect the materials. However, on the other hand, this is also a challenge at the same time. We face the problems related to high dimensionality of hyperspectral data. Computational complexity also increases significantly. Thus, many hyperspectral image processing pipeline indeed uses dimensionality reduction as a pre-processing step. Dimensionality reduction is something we will study after anomaly detection. However, there is another challenge with respect to this, that of course we cannot just reduce the dimensionality too much. Then we will lose out on the information, whereas working with the given all bands is also sometimes challenging. On the top of all this, some materials may exhibit significantly varying spectra. Furthermore, spectral characteristics may alter significantly given on the seasonal conditions and other factors. And these variabilities can also sometimes induce false alarms. Indeed, false alarms is an interesting phenomenon in case of anomaly detection, and we will come to a discussion about false alarms specifically later in today's lecture. We have to be also mindful about noise in the hyperspectral data. Remarkably, in the hyperspectral data, certain bands may exhibit lower quality compared to the others, such as water absorption bands often show poorer quality and are often excluded from further analysis. Thus, due to this band-to-band variation in quality, anomaly detection becomes even more challenging in the case of hyperspectral images. And this necessitates use of robust methods for hyperspectral anomaly detection. Now, talking about some basic pre-deep learning approaches for hyperspectral anomaly detection, let us first briefly discuss statistical anomaly detection. In the case of statistical anomaly detection, the model first models the background spectral distribution, and then the anomalous pixels are detected as those pixels that are deviating significantly from the background statistics. While doing so, often the background is modeled as Gaussian distribution. One approach that has been used quite a lot in the literature in this direction is Reed-Szäuly detector that measures Mahalanobis distance from the background. Similarly, PCA based anomaly detection has been used quite a lot in the literature. In the PCA based approaches, PCA models the dominant background components and then reconstruction error is used to indicate anomalies. One can also think of global or local variant of such algorithms. Those algorithms that we just talked, like background modeling, PCA based modeling. So one can think of global or local variant. Of course, the notion of global or local, this is based on the context of the spatial information, right? So let us discuss briefly the importance of spatial information. Spectral information alone may not be sufficient for hyperspectral anomaly detection. The neighboring pixels provide contextual cues. Spatial consistency helps us to reduce false alarms. Thus, what we see is that the methods that incorporate both spectral as well as spatial context, they improve robustness over the methods which are only looking at the spectral information. So we talked about the global variant and the local variant. Let us first think about what is the global variant. Global here in our case of the image analysis means our given image. We cannot, of course, just look beyond the given image, right? So in the global variant, they will use statistics from the entire image. This is effective for homogeneous scenes where we observe homogeneity over the entire image. That is, let's say like we are talking about modeling some forest. Often the background in the forest might be quite homogeneous. I'm not saying that, okay, we'll just see one class there. Of course, there will also be some spectral variability, but often it might be less compared to a complex urban area. Again, this of course depends on the type of forest and all, but what I am talking about is a general assumption. So in case of such scenes, the global variant may be quite helpful. However, the global variant will not work so well in case of the heterogeneous environments where we see in the image itself, given image itself, significant, in the given scene itself, significant variation. The local variant, this rather computes local background statistics. So instead of observing like the entire given image, let's say 224 cross 224 or whatever other size is, it rather looks at a localized area. Of course, it's not looking at just one pixel. That would be like a version of local, yet another variant of the local variant, where we are not looking at the spatial context at all. So we're not saying that, we are rather saying that, okay, like a local variant which looks at a part of the image. And here, let me be also clear that often it could be the case that, so what I'm saying, like, and given an image 224 cross 224, 64 cross 64, often it could be the case in the case of the earth observation, maybe we are not limited by those factors. maybe we can cover as big an area as we want. If that is the case, the global variant here will mean that still will mean that okay, like we are considering a considerably large area, whereas the local variant will mean that okay, we are considering a considerably confined area. Now, this local variance, this better handles the local spatial variability, and one can so you can think about the convolution operation itself, right? So this kind of slide in windows or convolution, this kind of operation can be used to estimate neighborhood distribution. So of course, I have not yet come to the discussion on the deep learning based approach. So that's why I'm using the more generic term sliding window. And the local variant can be somewhat more robust in the complex sense, where there is a strong variation, like there is an urban area next to this, and among the urban areas there can be variation, and next to this there is a suburban forest. So this kind of strong spectral variation here, the local variance can be useful. Actually, what is more useful is a combination of global and the local, which I'm just coming to that. Here, so talking about rather a combination of global and local variation, one can think about a dual window kind of approach. What is a dual window approach? In this case, the inner window captures more local variation, whereas the outer window captures rather global background information. And the contrast between the outer window and the inner window provides us more detailed information about what kind of anomaly we are looking at. So we'll come back to this dual window approach very soon again. However, let us slowly move to the deep learning for hyperspectral anomaly detection. The deep networks learn complex spectral as well as spatial patterns, and the nonlinear representation improve anomaly detection significantly. So let us now think about how we can use the deep networks. Most of our discussion is, of course, related to the CNNs. So how we can use them to detect anomaly. And remarkably enough, what we'll see is that most of the code ideas are similar to what we have already discussed. So we'll again use the approaches such as reconstruction, as we have discussed in the case of PCA, or this dual window, let's say. So this kind of ideas we will reuse, however, in the context of deep learning. So let us look at how we can do that. So let us start from the reconstruction concept. And the very obvious candidate for reconstruction in the case of anomaly detection is autoencoder. Autoencoder helps us to accomplish learning in unsupervised manner. With autoencoder, that is combination of an encoder and a decoder, we can reconstruct the normal background spectra. And the assumption is that the anomalous pixels, they will show large reconstruction error. Thus, the background pixels, they will have smaller reconstruction error, anomalous pixels, larger reconstruction error. And given this reconstruction capability of an autoencoder trained on normal background spectra, of course, we can thus detect anomalous pixels. And now let us tweak autoencoder for the dual window concept. So in the dual window concept, recall what we are doing. We had outer window, we had inner window, right? So the same thing we can do using autoencoder. We can have two different versions with a larger window size, with a smaller window size. The autoencoder with the larger window size, so that will be modeling the background, whereas the autoencoder with the smaller window, the inner window, this will model the smaller objects or like more localized context, I would say. Now think about the reconstruction error of outer window autoencoder, reconstruction error of the inner window autoencoder, and consider different scenarios arising out of it. So how many scenarios could arise out of it? So reconstruction error can be small, let's say, right? Reconstruction error can be large, and we are talking about two different window size. So this will mean that we have 4 combinations, right? So if the reconstruction error is small in both cases, using both the outer window and using both the inner window, in that case, probably we do not have an anomaly, right? Whereas, think about reconstruction error to be high with both outer window autoencoder and the inner window autoencoder. In that case, probably we have an anomaly, right? Whereas on the other hand, think about the 2 other scenarios and think about this, that which scenario, like one of them high, one of them low, what does this imply? So this leads us to different interesting scenario. And now, to capture the spatial context in a better manner, what one could do is that instead of using a vanilla version of autoencoder, one could adopt convolutional autoencoder. So this will enable us to capture the spatial context even better. Similar to the autoencoders, generative adversarial network can also be used for hyperspectral anomaly detection. The ideas remain quite similar to the autoencoder. So I will skip discussing into the more details of using GANs for hyperspectral anomaly detection. However, you can think about this, like how will you use GAN, how will you use the generator, how will you use the discriminator. This is quite similar to the autoencoder and quite straightforward. We can exploit 3D CNN for hyperspectral anomaly detection. 3D CNN will jointly process spatial and spectral dimension and learn more effective spectral spatial anomaly patterns. From all this, one can also come up to a weakly supervised approach for hyperspectral anomaly detection. So how would such a weakly supervised approach look like? One can potentially start with performing dimensionally reduction on the input data. So this is more of an optional. Let's say you applied it. Now, what one could do is apply one of the existing ideas for first level anomaly detection. So let's say we are talking about like a large area in consideration. So for this large area, we apply one of these existing ideas for first level anomaly detection. Now, some pixels or some objects are detected as anomaly. Now, on the top of this, one can apply some post-processing. This post-processing could also be, let's say, some human intervention for refinement of the anomalies. So indeed, there could be like a large number of false alarms and one could just give it to human annotators. Now, okay, these all qualifies as anomaly and some of them do not qualify as anomaly. Of course, you will have to adjust your algorithm in such a way that, okay, probably you are more prone to detect false alarms and you are not prone to miss out on the anomalies. Now what one can do is, with this refined data, one can now train a supervised classifier. Maybe it's a 3D CNN module. We have talked about like the possible classifiers in the context of hyperspectral image analysis before. So one of those supervised module we can now train with this data which we have obtained using another anomaly detection approach and with some refinement. And this will enable us to at least detect these possible anomalies on this particular geography. So it might not really work, like if we are like, let's say you have defined this approach for, let's say, desert area. So maybe like it generalizes to nearby deserts, but probably it will not really transfer well to some urban area, because in the urban area the anomalies itself may be different. So what we are doing here, think of this in a way we are converting the anomaly detection to a target detection approach. We mentioned before that the false alarm rate is one of the critical aspects in hyperspectral anomaly detection. High false alarm, of course, reduces reliability, whereas on the other hand, also one would agree that missing out on the anomaly may be of more concern. So it depends again on the exact application, but in the most cases, like let's say we are interested in some kind of defense surveillance, so maybe we don't really want to miss out on the anomalies, and in this case we may be okay with some false alarms. So what could be a possible approach here is that first to go for rather high number of false alarms, whereas to ensure that, okay, we do not miss out the anomalies so much. And then on the top of this, somehow we can use some kind of post-processing. Again, the post-processing itself can depend on like exact scenario that we are considering. Often it could be the case, like a lot of anomalies detected from, let's say, cloud. So, okay, we have some cloud detection pipeline simultaneously. Or a lot of anomalies are happening due to a particular class. It could be, let's say, like anomalies are happening in the water. So maybe we have some kind of water detection algorithm, and with that we have the land cover map. So we just remove those pixels which belongs to water. So this kind of post-processing, and it will need some background knowledge about the target area, of course. Let us briefly discuss a couple of data sets that have been proposed in the context of hyperspectral anomaly detection. One such dataset is Airport Beach Urban ABU dataset with this particular scenes, and the dataset is mainly collected using the Abedis sensor. Similarly, another popular dataset is HYDEC. This is captured over an urban area in United States. The image is of size 80 cross 100 pixels, and depending on what pre-processing has been applied, the number of bands may vary. However, most research works, if you see, they consider it as 175 bands image. The ground truth of this dataset includes 21 anomalous pixels, which are mainly cars. So again, the discussion on this dataset makes the point clear that how the existing datasets on the hyperspectral anomaly detection, they are so small, which means that okay, we have to of course approach this problem in unsupervised manner, and we really don't have, of course, one thing is like, okay, this is anomaly detection problem, which we talked before, that this is not target detection problem, which automatically implies that okay, we have to model this as unsupervised problem. But also this dataset size and all, this also restricts us from really processing it as a supervised approach. Rather, we have to go ahead with some kind of unsupervised approach, as we have discussed in today's lecture. So we'll stop here. Thank you.